So at this point, we've talked about how we can describe the relationship between two different variables in terms of strength, from very strong to weak to no relationship, and talking about direction. Is it direct or is it indirect? Positive or negative? Inverse or But really, we can only talk about these relationships in that superficial manner. One way that we can describe and interpret correlation coefficient in a much more precise way is by calculating and interpreting the coefficient of determination, which is also denoted as big R squared. And the coefficient of determination describes the amount of variance which can be accounted for by the variance in another variable. Huh? Well, thinking about this, thinking about drinking alcohol and tobacco, we are going to see some variability, some differences in a sample that we have. Let's say we have a sample of 10 students, and we ask those 10 students, okay, at what age did you start drinking and at what age did you start smoking? Well, hopefully you're going to have 10 different answers, maybe a couple that are going to be the same, but for the majority, we're going to have some variability among our 10 students. And the idea behind correlation coefficient is that we want to see whether or not there is a relationship between these two variables. And the way that we do that is by looking at the individual scores and how much variability there is. So our calculation for coefficient of determination is simply big R squared is equal to little r squared, where little r is our Pearson's product moment correlation coefficient. So thinking about our previous table that we saw, the relationship between drinking and smoking for the first time came out to R equals 0.452. So go ahead, take a moment, and calculate the coefficient of determination when R is equal to 0.452. Alright, so did you calculate it? Well, here we go. Big R squared is equal to little r squared, so we take little r, which is 0.452, square it, and we get 0.2043. This number here indicates our coefficient of determination. But in order for us to interpret the coefficient of determination, 0.2043, we must turn it into a percent. So how do we convert this number to a percentage? Multiply by 100. So when we do that, we then go ahead and use this template to interpret our relationship, our coefficient of determination. Variable x accounted for so much percentage of the variance in variable y. So you must convert your coefficient of determination to a percentage by multiplying it by 100. This is what you do when you are interpreting your coefficient of determination. If I'm just asking for your coefficient of determination, give me the decimal. But if you're going to use it in an interpretation, you must report it and calculate it as a percentage. So here we go. Age of first use of alcohol accounted for 20.43% of the variance in age in first use of smoking cigarettes. Variable x was alcohol, variable y was smoking cigarettes, and our coefficient of determination was 20.43%. So this is visually what's really going on when we think about coefficient of determination and the variance that these two variables share. We have variable x, and we have variable y. And if there's no correlation, then there's no overlap. If there is some correlation, the stronger it is, the more overlap there is. In this case, we only see about 20.43% of variance that's shared. So we're really only going to see about 20.43% of overlap between variable x and variable y. So then what about all this other stuff that isn't accounted for? Well, this is what's called the coefficient of alienation. It describes the amount of variance which cannot be accounted for between these two variables. Right? If you think about the age that somebody first drank alcohol and the age that somebody first used cigarettes. Well, there can be so many other factors that can contribute to somebody drinking for the very first time, or somebody smoking cigarettes for the very first time, that it's not necessarily because of drinking or because of smoking that contributes to somebody drinking for the first time or smoking for the first time, right? There can be so many other factors out there that may have led to somebody drinking and smoking. This is what we describe as the coefficient of alienation. And the equation for this is simply 1 minus our coefficient of determination. So given our coefficient of determination here as a percentage, we can simply throw this in here using the decimal. 1 minus 0.2043 gives us a number, turn that into percentage, and that's simply now the percentage that is unaccounted for between the age of first use of alcohol and age of first use of smoking cigarettes. Here's a sample question. Here are two variables again. Take a look here. R squared linear equals to 0.204. Notice this number? So first question, what is the test statistic? Little r. Well, how do we do that? We have big R squared here. So how do we get back to little r? Well, we could simply do this. So plug and chug. What do you get? It should match up to what we started with in the previous slide. What kind of correlation is displayed? Positive, negative, or no correlation? Well, without even looking at the number, let's just look at the scatter plot. What do we see? What's happening to the line as we move from the right on the x-axis and as we go up or down on the y-axis? This is demonstrating a positive correlation. What is the strength of this correlation? Well, if we're looking at the scatter plot, we see there's some dispersion, right? But we see there's also a lot of clumping together. So we really, at this point, can't say too much as far as the strength, so we're going to have to turn to our correlation coefficient test statistic itself, little r, to make that interpretation. And if you calculate it correctly, you should get 0.452, and when we look at the table at the beginning of the lecture, that corresponds to a moderate correlation. So this is a moderate positive relationship between age first drank alcohol and age first smoked cigarette. Alright, so the last things about this chapter, limitations. Two main things. The first thing, third variable problem. So if you think about all the different types of bivariate relationships that we've talked about as far as examples here, causality between these two variables cannot be assumed because there may be some other measured or unmeasured variable that could be affecting these results. We call these variables confounding variables. Again, when I talked about something that may be contributing to the unaccounted variances between these variables, between somebody drinking for the first time or smoking for the first time, there may be some other things, right? Maybe your parents drank all the time. Or maybe your parents smoke, so you have access to cigarettes, compared to somebody who has no access to cigarettes and their parents don't drink at all. They're not going to have access to liquor or cigarettes, so that may contribute to somebody's age being younger or older, right? So accessibility could be a confounding variable. There can be other things that contribute to these relationships, to these correlations that we may not be measuring or may be completely unknown to us. So we need to be careful about these relationships, about correlations. We can't really imply or talk about cause and effect, which brings us to our other limitation, causality. Correlation coefficients really say nothing about which variable caused which and which variable came first, right? They think about the whole idea of which came first, the chicken or the egg? Same thing kind of holds true when you think about correlation coefficients and bivariate relationships. We really cannot say that if somebody drinks at a young age, that they're going to smoke at the same age. Even though we may find a strong positive relationship, that does not mean that X causes Y, nor does that mean that Y causes X. And we really can't figure out which one happens first. All we really know when we're calculating and interpreting correlation coefficient, whatever type it is, it's really just talking about how much variance is shared between these two variables. So in closing, in summary, correlation coefficients are used to examine the relationship, the correlation, the connection between two variables. Thus, it's called a bivariate relationship, bivariate correlation. And really the one that we're going to be focusing on that you'll be hand calculating is the Pearson's product moment correlation coefficient, which is signified as little r, and we use two continuous variables, interval ratio. And this is the funky formula that we're going to have to know how to calculate and work through. Remember, when you're showing me your work, you don't have to show me every little single multiplication or square or addition that you did. As long as you fill in the table appropriately, put in the correct headings, fill in the table with all the numbers, and then just plug and chug into this insane formula. Work through the calculation and give me your final answer. Lastly, it really, aside from being able to talk about the strength and the direction of these relationships, what's a more precise way of determining, the more precise way of interpreting it is using the coefficient of determination, which explains how much variance is accounted for and is shared between these two variables, and also using the coefficient of alienation, which describes how much variance is unaccounted for and is not shared between these two. And one very, very important thing, we have confounding variables, and correlation coefficients never, never imply causality. All right, good luck studying.